Welcome to today's webinar. My name is Aimide Opong and I will be your co-host today alongside Mimi. For those of you joining us for the first time today, I want to say a warm welcome to you. Thanks for joining us. I hope you enjoy this webinar. I've been looking forward to it and I hope you enjoy it too. For those of you that have joined our previous webinars, our other events, I also want to thank you very much for joining us. We really appreciate you and your support through it all. We want to say a big thank you as well. For those of you who don't know about AFBE, AFBE is Association for Black and Minority Ethnic Engineers. The organization is aimed at supporting professional and student engineers to succeed in the engineering industry. If you want to find out more about AFBE, which you should do, you could check us out on the www.afbe.org.uk. So yeah, I've been looking forward to today's webinar, the nitty gritty, with Mimi. I promise it's going to be very engaging, and I do encourage everybody to engage in this quiz. There's going to be a quiz, so please do engage. You don't have to be a concrete whiz, just take part and enjoy it. So yes, I will pass it on to Mimi to take over.
Hi everybody, thank you for coming to my webinar and welcome to the nitty gritty concrete quiz. So as Aimide said, I would encourage everyone to participate. You don't have to be a concrete whiz. It's just, for me, it's just for participation. You learn something new. So yeah, so I'll begin. There's health and safety and some warnings first. So health and safety first being, obviously we're in unprecedented times of COVID-19. So I hope everyone is following the government guidelines, and if they're leaving the house, it's for the bare necessities. That is my first joke of the session. And my second is a warning, so there's some chemistry. So I remember being at school and not being a massive fan of chemistry. So with this presentation, I have tried to water it down quite a bit so we can all understand. So it shouldn't be too bad. So that's before the quiz. I'm gonna talk a bit about me, give 3 points about concrete, and then I'll start the quiz and I'll give some answers at the same time. And then at the end, I'm gonna do some more concrete facts, which is actually essentially about my dissertation. So about me. My name is Mimi-Isabella. I graduated from the University of Portsmouth in 2018 and I studied civil engineering. Currently, at my job, I'm a materials engineer, specializing in concrete. However, I don't just do concrete. I also do other materials such as clay, sand, gravels, etc., etc. And I work for an organization called Sir Robert McAlpine. So my job basically is that how can we ensure that the materials that we are using are correct for the project? So I do that by conducting materials testing, conducting site investigations, reviewing specifications according to certain standards that you'll find out later on, and basically just ensure that our projects will be sustainable for the near future. So why concrete? People always ask me. So like most people here today probably have no interest in concrete whatsoever, or wasn't really sure about it, or just know it was grey. So that was kind of me in 2014 when I started my degree. What I enjoyed about concrete was that it's the complexities of concrete and how it can be manipulated for its intended use. And also because concrete is fantastic. And for me as well, I wanted to go into materials because I was very interested in sustainable development. And I knew that materials engineering would probably pioneer this. So that's an introduction to me, just very brief. So name something that you know that's made out of concrete. So if you type it in, it will come up on my screen. So as you can see before, there was various different infrastructure and building that people were talking about. So concrete is actually the most man-made construction material in the world. And with knowing that, you saw that there's different things that concrete can be used for. We can now know that not all concrete is the same. You can't use the same concrete you're going to use for a building that you'll use on the road. And also, if there's one thing I want everyone to take away today, even if it's just one, if you don't listen to the rest of this, this is the only thing you take away, is that cement and concrete are not interchangeable terms. If you want to annoy a civil engineer, mistaken cement and concrete, they are not the same, but I'll divulge into that later. So the quiz, just as how I did now, I'm going to ask a question and then I'm going to give you a couple of moments to answer it. And then after that, I'll give an answer straight away. And then that's how the quiz will continue. Like I said, it doesn't have to be a concrete whiz. Please just give it a try. It's just all a bit of fun. So let's get cracking. That is my first concrete joke. And it's the best one I had. So question 1, what are the primary components of concrete? Is it A, cement, wood, aggregates, B, cement, water and silicone, C, cement, water and aggregates, or D, cement and water? Now, before you answer, for the non-civil engineers amongst us who are not really sure what aggregates are things like cement, like sand, gravel and crushed rocks, etc. Most people did all right. Yeah, so most people did okay. So the primary components of concrete are, answer C, cement, water and aggregate. So congratulations to those who got it correct. So concrete is actually a mixture of 2 components. It's a mixture of aggregates and a paste, and that paste being made up of Portland cement and water. So as you can see on the diagram on the left, it's made up of 8% of air, 7 to 15% of cement, 14 to 21% of water, and 60 to 75% of aggregates. Now, I like to liken making concrete similar to baking a cake. So I'm going to use the analogies together. I hope no one gets confused. So with concrete, essentially, like a cake, you get all your ingredients, you mix it together. So you use the concrete mixer, you put your ingredients in the concrete mixer and you mix them together. Then after that, you'll put them in a concrete molds. So the molds can either be long steel beams, cylinders, or cubes. So these three types of mold are used to imitate the structural components that can actually be built on site. So that'll be long beams, some sort of cube, or in a cylindrical shape. Once that is completed, they'll be put on the vibrating table, which has its British standards. So why do we put on the vibrating table? So you put the concrete molds onto the vibrating table because you want to remove any air bubbles or inconsistencies within your concrete and make sure your concrete's actually set in the right shape of the mold, essentially. Once that is complete, you'll leave your concrete to set overnight. Well, I did it overnight. You leave concrete set overnight, and then you'll put your concrete into a curing tank. So like cake. So you'll get all your ingredients, you mix it together, you put it into the baking tray, and then you put it in an oven. However, an oven and a curing tank are not the same thing, but we'll get back into that later. So back to the beginning, I said that concrete and cement are not the same thing. So cement is an ingredient used inside of concrete, and concrete is the final product. So I hope everybody now understands that. For those who didn't know, I hope that's more than clear now. So the next question is, how many days does it take for concrete to reach its required strength once left to cure? So like a cake, you'll put it in an oven. Cakes obviously take, a couple of hours, unless you leave your cake in for days. Don't tell us, just keep that to yourself. But concrete takes a number of days for it to reach its required strength. So how many days do you think that takes? Is it A, 100, B, 7 days, C, 28 days, or D, 32 days? So the answer is actually C, 28 days. So I think it's important to understand what is actually happening during those 28 days, what gives concrete its compressive strength. So an important thing to know as well is that concrete doesn't dry over time, it hardens over time. But I will come back to that later on. So what is curing? Curing is defined as providing the adequate moisture, temperature, time, and time allows for concrete to achieve its desired properties for its intended use. So there's water in the tank, and this water is about 20 degrees-ish. So what's happening inside of the concrete? So in the curing tank, a reaction takes place between the water and the cement. This is called hydration. So back to my first bullet point about concrete not drying over time, but hardening. If you were to dry concrete, that would imply that you're actually removing the water from the concrete, and that's not correct. Because water is actually the most important component in concrete, so it's essentially needed. So too much water would reduce the strength of the concrete, but too little water will make the concrete very stiff. So it'll be hard to pour on site, hard to put in the mold, etc., etc. Now, let's get to the science. What I think is important when I explain about hydration and cement is that I think it's very important to understand the chemical composition of cement to understand hydration. So typically, cement is made up of 5 compounds. However, I know 2 of them. And thank God, because the 2 of them I'm going to talk about are the most important ones. They're called tricalcium silicate and dicalcium silicate. So most people hear in the engineering world that with concrete, the first 7 days of the curing process is the most important. The fastest part of the reaction is. And tricalcium silicate is responsible for 7th day strength. Dicalcium silicate is responsible for the later strength. So what happens? So tricalcium silicate in the cement, when it reacts with water, produces hydrates and hydroxides and also releases some sort of energy. So when the hydrates and the hydroxides are produced, they form chemical bonds, therefore compacting the concrete much more, therefore giving it strength. Now, that's in the first 7 days. So dicalcium silicate is responsible for the 7 to 28 day strength. Essentially, they have the same reaction with calcium silicate, with hydrates and hydroxide ions. However, it also combines with the 3 other compounds in cement. And this happens at a later stage, but it also happens at the beginning as well, but it just happens much slower. And that's what's happening. So as I was doing this quiz, I found some concrete jokes along the way. I hope, people understand, but so a man walks into a bar holding a chunk of concrete and he says, "I'll take one for me and one for the road." Sorry, I found that funny. Maybe it's just me. Obviously, I can't hear anyone, but I hope everyone is falling off their chairs right now. So we all heard in the news the environmental impacts of concrete. Concrete's not good for the environment, etc., etc. But why do you think concrete is not good for the environment? Is it A, waste concrete is thrown into the sea? B, when concrete is poured on site, it releases toxic fumes? C, the production of cement releases carbon dioxide into the atmosphere? And D, concrete removes oxygen from the atmosphere? So the answer is answer C, that cement production releases excess carbon dioxide into the atmosphere. So someone has asked me recently, if there's already carbon dioxide in the atmosphere, how does cement production affect the atmosphere? And I said, okay, well, excess. So anything in excess is not good. So when you increase levels of carbon dioxide into the atmosphere, this increases the rate of the greenhouse effect. Now, I'm hoping everybody knows what the greenhouse effect is, because that is another webinar, and it's not this one. So essentially, it increases the effect of global warming, so it heats the earth up. So now that we know that it's carbon dioxide that is causing an issue with the atmosphere in terms of cement production, approximately what percentage of the world's carbon dioxide emissions do you think are sourced from cement production? Is it A, 8%, B, 5%, C, 45%, or D, 21%? So the answer is A, 8%. I really do believe if it was 45% of the world's carbon dioxide emissions, we wouldn't be using concrete ever again, ever. So importantly, I think people should know how cement is produced. If it's causing this much problem to the environment, we should know how cement is produced. So Portland cement is an industrial standard cement that we tend to use. And it's a mixture of burning limestone and clay together at extremely high temperatures. So limestone is quarried, it's crushed into small pieces, and it's mixed with sand, clay, and iron. Then it's ground to form powder, and this powder is called cement. So cement is very, very important to the concrete industry because it's actually used in 98% of concretes globally, with 4 billion tons produced each year. So this is clearly an issue. So what happens during this? So when limestone is heated at high temperatures, it goes through a process called calcination. Therefore, the limestone is calcinated, producing CaO, which is lime, and waste CO2. So as you can see in the equation below, it's the waste CO2 that's causing the problem. There's nothing that we can do with it. It just goes straight into the atmosphere. And that's that. Next question. So does concrete work, so loam concrete, just bog standard concrete, work better in tension or compression? So is it A, tension, B, compression, or C, tension and compression? I promise you I will not play the music again. Okay, so most people said compression. Cool. Right, so for the non-physicists amongst us, I think people would like to know what tension and compression forces are. So basically, every material can handle a certain amount of tension and compression, and these are called stresses. So a tension force pulls materials apart, and a compression force squeezes materials together. So that's the very bog standard, basic way of explaining both of them. So why is concrete better in compression than it is in tension? So concrete is great because it has this high compression resistance. So it's able to support loads of weight. So hence why loads of concrete building foundations are made of concrete to support your buildings such as the Burj Al Khalifa, etc., etc. So this is due to the concrete's compact nature. It has adhesives and aggregates adding to the friction factor, so it resists compression. So essentially, when you stand on concrete, it doesn't capsize because you have to push down on the cement and also the aggregates to really push down to get to the bottom of it. So it takes longer to do that. However, if you smash concrete with a hammer, it only has to pull apart the adhesive factor, which is the cement. And that's the only thing that is resisting that tension, just the cement holding it together. However, concrete alone is a very brittle material. So just normal concrete, if you smash it, like I said, it falls apart. So in building design, a composite material is used to counteract that concrete is weaker in tension. Actually, top tip, concrete is actually not weak in tension, it's just stronger in compression. So what we tend to do in building design is that we reinforce concrete with steel bars, and this concrete is now called reinforced concrete. So what is reinforced concrete? I'm sure somebody asked, I heard it, although everyone's on mute. So reinforced concrete, essentially basically putting steel bars inside of concrete. So if you look at the picture on the left, is what we do on site. Those steel bars are designed by engineers, so they don't always look the same. It's dependent on the building size, the surface area, the amount of load your building has to take. So this affects the length and the thickness and the shape of those bars. So they lay them down like so, like you see in the picture on the left. Then after that, you get your concrete pump and you'll pour your concrete on top of that. So what happens is, when the concrete is poured on top of it, it hardens around the steel and it forms a very strong chemical bond. So now it's a composite material. The composite will resist the squeezing, which is the compressive strength, and the steel will resist the bending, the tensile strength. So now your reinforced concrete is now good in tension and compression. Next question. So most of us have done science or done scientific experiments. You know, there are British standards associated with everything that we do. This is the same for concrete. So what do you think are the British standards that are used for concrete? Is it A, the BS 8500 and the BSEN 207, B, the BS 6500 and the BSEN 203, C, the BS 6501 and the BSEN 206, or D, the BS 8500 and the BSEN 206? So the British standards that we use are the BS 8500 and the BSEN 206. So that was answer D. So what is the BSEN 206? So this is the European standard for concrete. Essentially, it specifies requirements for constituent materials of concrete, properties of fresh and hardened concrete, and their verification. So what does that mean? So essentially, if you want to design a concrete of a certain strength, it will tell you the materials to use, how much water to put in, what type of cement to put in, and also the test that should be conducted on that when it's fresh and when it's hardened. And also, if you receive a concrete from your concrete producer, if you want to verify that your concrete is the concrete that you've asked for from them, it tells you how to do that too. Now, the BS 8500 is the complementary standard to the BSEN 206 and is split into two parts. So essentially, if the BSEN 206 is this big, the BS 8500 is in two parts, but it's much smaller. So which one does everyone think I'm reading? I read all of them. So the BS 8500 is essentially the same thing. So part one is the guidance for the concrete buyer. So if my organization asked another organization to make us some concrete, it describes, so I've asked the organization for concrete, it describes how we can, when they send it back to us, how we can verify that concrete is what they've said it is. Did someone say something? No, okay. And the BS 8500 Part 2 is for the people who are making the concrete. So when my organization asks another organization, could you please make this concrete for us? This is what we wanted to, this is the properties that we wanted to have. So it tells them how to do that. So how much water to put in, what aggregates to put in, what size of the aggregates to put in, etc., etc. And that's that. And there are more standards. Obviously, when we do our doing our testing on fresh and hardened concrete, there are various standards that are associated with those as well. So I personally didn't design this, but I found this on Instagram and I did giggle for a few minutes, and I'm sure everyone else is laughing as well. However, everyone's on mute, so I can't hear.
They're laughing.
Next question. Huh?
They're laughing.
Question 7. Which of the following is a test that can be conducted on fresh concrete? Is it A, the California bearing ratio, B, a slump test, C, the compressive strength test, or D, the plasticity index test? So I'll give people a few minutes. So the answer is a slump test. So what is a slump test? I heard somebody say there, everyone's on mute. The slump test is a means of assessing the consistency of concrete. So essentially it's a test to say whether you've put the right amount of water into your concrete. So as I said in the beginning, that water is the most important component when it comes to making concrete. And there's a whole test dedicated to finding out. So if anybody wants to confirm what I'm saying, you can read the British Standard, which is the BSEO 12350 Part 2, testing fresh concrete slump test. So how do you perform a slump test? You need your concrete, obviously, your metal funnel and a metal rod and a ruler. So once you're finished mixing your concrete, the concrete mixer, like we discussed in the beginning, you'll take a volume of that, which you'll find in the British Standard what volume that is, and then you'll put it into your metal funnel. So you put it in 3 layers. So you put the first layer in, then you use your metal rod and you'll stump it 25 times. Then you put your second layer in, then again you'll stump it 25 times. Then you'll put the third layer in, and then you'll stump that 25 times. Why do we do this? This to ensure that it's compact and also imitates how it would be on site, basically. So once you do that, you'll use the arms of the concrete funnel, you can see in the picture above, and then you'll flip it over, and then you'll slowly raise it. When you take off the funnel, picture below shows one of the 3 outcomes that you can potentially get. Most people are aiming for a true slump. True slump means you potentially have the right amount of water in your concrete, and then you have the other extreme where it completely collapses. This will mean that your concrete has too much water in it, and then you'll need to go back to your mix design to decide if you need to take some more water away and deciphering what properties you want your concrete to achieve. And the middle, you'll probably need to go back to your mix design. It's probably just maybe give or take some water, probably. But that's depending on the properties that you're trying to achieve from your concrete. So why do we test on concrete? We test on concrete because you want to look at factors such as strength, consistency, the unit weight, the air content, and temperature. So by testing on fresh concrete, you're actually able to detect changes that may affect your concrete long term. So if you have too much water and you start to cure your concrete, and then you may not be able to achieve the properties that you actually set out to achieve because maybe there's too much water, but you wouldn't know that if you didn't test it whilst it was fresh. So essentially you're saving time and money, which is what we want to do in construction. Time and money. Time is money. So next question. So what is the largest concrete structure in the world? This question will let me see if people have left the UK, left London, ventured out a little bit. I'm only joking. But A, is it the Burj Khalifa in Dubai? B, the Colosseum? C, the Three Gorges Dam? Or D, the Hoover Dam in North America? So the answer is the Three Gorges Dam in China. So the Three Gorges Dam is a hydroelectricity dam. So this generates electricity essentially through hydropower. It was completed in 2003 and it stands at 185 meters tall, approximately 2,300 meters long, and it is 40 meters wide. So that's a lot of concrete, basically. How it generates hydroelectric power, I'm not exactly sure. That is something that we can all go and look up later. So conveniently, as I was looking up the concrete dam, I found this concrete joke. So two fish swim into a concrete wall. One turns to the other and says, damn. Sorry. The fact that everyone's on mute, it seems like I'm laughing on my own, but I'm sure everyone's falling off their chairs right now. So we've spoken about a lot of sectors about concrete. However, I did forget to ask in the beginning, how far do you think the origins of concrete date back? Is it A, the Romans, B, the Egyptians, C, the rise of the British Empire, or D, the early Nigerians? So, for those who had no faith in Nigeria, the answer was the Egyptians. So, as far back as, so concrete actually dates back as far back as 3000 BC. So the Egyptians actually used lime and gypsum, which is now one of the components of concrete that I spoke about earlier. Lime and gypsum, which is actually very similar to concrete. So the pyramids that we know today, the pyramids of Giza, don't know how people pronounce it, Giza or Giza, the Egyptians used lime, gypsum, straw and sand, hence the colour. So that was their early forms of concrete. So it's quite nice to know when I discovered that actually the pyramids are made of some sort of concrete. But it's obviously not the concrete that we use today. Now, lastly, and this is an important fact that I think that people should know about concrete as why it's used in a lot of building design. So for me, this is my most important fact. Concrete does not burn, it cannot be set on fire, and it doesn't emit toxic fumes when affected by fire. This is due, this is due to concrete's excellent performance due to its primary components. When the cement and aggregates are binded together, when you mix them, they become inert. So inert meaning they do not react with anything. So this is very important for building design, building design and fire safety design. Also, concrete has a slow rate of conductivity, heat transfer. This enables concrete to act like a fire shield and also protects itself from damage. So what that means is, because concrete is a very dense material, so a concrete block, it's very dense. When you set fire to it, it takes a long time for the heat to dissipate through the rest of the material. So therefore it acts like a shield. So only the face of the concrete will essentially take most of the damage, if it does damage. So whilst I'm doing my dissertation, I did a short study on a school in Cheshire. Typically, a fire can reach about 500 degrees in 10 minutes and 950 degrees in 1 hour. So this school in Cheshire, their whole department burnt, well, the whole department was set on fire. So this was 18 classrooms. However, the impact of this fire was very limited because of the fire resistance of the concrete structure. So essentially, the structural integrity of the building was still there. It was only the furniture and the extra, maybe the paint, etc., inside that was damaged, and the plasterboard, etc., that was damaged. So when I was reading the article, one of the teachers was saying that they were afraid that they'll have to postpone teaching until next year, etc., etc. However, rather than taking a year, they didn't have to demolish the building to rebuild it up again, because the building still had its structural integrity and most of the classrooms were actually maintained. All they had to do was repair the concrete and it was ready for the following term. So rather than waiting a whole year, all they had to do was wait 3 months and they were back in their classrooms again, good as new. So that's coming to the end of my webinar. Just a few, so things that we have covered today. We looked at the constituent materials of concrete, concrete curing, concrete and the environment, reinforced concrete, concrete testing, concrete standards, the history of concrete, and concrete and fire. Now, I think my webinars lasted about 40 minutes. So you've learned all this in 40 minutes. It took me 4 years to learn all of this. So I think I'm doing everyone a favor. So congratulations.
Thanks so much.
So congratulations for making it to the end and not leaving. And I am very fun at parties, number one. This is usually me at a party.
Thanks for
Final question. Don't run yet. Final question is importantly for me. Did you learn something new today about concrete? Yes or no? If you say no, I'm going to assume you have a civil engineering degree.
Yes, I did.
You did? You did?
Yeah.
Absolutely.
You did?
Yes, I did.
Oh, I'm so happy to hear that.
I learned something.
It was very good.
Thank you. I'm really happy to hear that.
Yeah, thanks.
You're welcome. So, AFBE, we have Facebook, Instagram, Twitter, and YouTube, so you can follow us on all our social media. If you would like to work with us, we have a website, www.afbe.org.uk. And if you'd like to get in contact with us, we have an email address, info@afbe.org.uk. Thank you for coming to my webinar, and thank you for listening to my presentation on concrete. And I think now we all know why I love concrete.
Thanks, Mimi. I'm sure I could go on site now and drop some new gems. And
if anyone asks where you got your information from, just don't say me.
Okay.
And if anyone wants to cross-reference my information from 2 books, from the ICE Manual of Construction Materials, this is another one of my Bibles alongside the BSEN 206 and the BS 8500 Part 1 and Part 2, now that we all know what those are. And this comes with 2 volumes. And this is not an advert for the ICE. I've not been paid to do this, but just in case.
I think they should have you as the ambassador now, so I'll put in a word.
Well, thank you so much for coming.
Thanks, Mimi. I think now we can take a few questions. If anyone has any questions.
So Mimi, sorry, I have a question for you. What's your favourite building?
My house. I'm joking. What's my favourite? Probably Amazon's headquarters in Shoreditch, because I was there when they built it. So it's always going to be something special to me.
Oh.
Thank you, Chanel. Where does the name Portland Cement come from? I believe it's from the Roman times. Please do not go back and tell someone that I said that. But I believe it's from the Roman times. I can't remember, I'm sorry, but I believe it was from the Roman times that they used Portland cement, but I cannot remember. I'm so sorry. I should know that.
Any more questions?
I hope not. Any more questions? No? Oh, and thank you to all my friends who attended. I really appreciate it.
I was waiting for my shout out.
Oh, Jamie, thank you.
Yeah.
And mine, please.
Oh, Vanessa, thank you. But if no one has any questions, great for me.
Everybody's saying how well the presentation went, and I really agree.
Yep.
Before we close, just wanted to tell everybody about our upcoming events.
Yep.
So our next event will be coffee break. We'll have 3 sessions during the coffee break at 9, at 12, and at 5. If you'd like to network with some of AFB's members, or just come and have a chat, please do join in the coffee break, and that will be
there is a session on the 2nd of May, Saturday, on physics.
Okay. Yes.
Yeah. So, the physics of fascinating physics of everything, for 12 to 16-year-olds.
Yes. Thank you for reminding me. If you have any relatives or friends that would like to attend, please do share with them the event. Please follow us, AFB, on all our social media, Instagram, Twitter, YouTube, and hope to see you soon. Hopefully next time myself and Mimi will be dancing to the countdown